Hi everyone, I'm Akanksha and I'm going to talk about our paper, A Moment in the Sun, Solar Nowcasting from Multispectral Satellite Data using Self-Supervised Learning. This work is a joint collaboration with Trapit Bansal and David Arvin. And this work was done as a part of my doctoral thesis at UMass Amherst. While presently, I'm a postdoc at Sierra, Colorado and the NSF AI Institute, where I work on developing ML models using satellite data for climate applications. Let's start by breaking down the title of the talk. Solar nowcasting means predicting solar at short time scales, like in the range of 0 to 60 minutes. While we use data from multiple channels or wavelengths, that is the multispectral bands from the GOES 16 satellite at intervals of 5 minutes. And we use self-supervised model, which means that we leverage the information from the unlabeled satellite data and then apply the extracted features on the site-specific solar data. With that, let's dive into the talk. The Earth's global energy demand is roughly around 20 terawatts, while the terrestrial solar radiation is 10,000 times more than that. This means that more energy hits the Earth's surface in one single hour than the entire world uses in a whole year, making solar the largest resource by far amongst all the available finite and renewable energy reserves. The obvious question here is, if solar is so powerful and a source of virtually unlimited clean energy, why are we still using so little of it? This is because electricity systems are a really delicate balancing act in some sense. We have controllable electricity generators feeding power into the grid. And on the demand side, we have consumers who are pulling electricity out of the grid. The utility needs to make sure that the power going in equals the power coming out at every single moment. Failure to do so might either result in power blackouts or power surges. While the power from the traditional power generators can be controlled by regulating their fuel supplies, the consumer demand remains uncertain because humans have free wills and they can anytime turn their electrical devices on or off. But with the rise in the rooftop solar installations, consumers are becoming prosumers by both generating as well as consuming energy. So now, in addition to the traditional power generators, we also have solar feeding power into the grid, whose production is dictated by weather. So now we have this complex balance between the supply and the demand, where the supply is potentially unknown ahead of time, and the demand is also potentially unknown ahead of time. So the only way to control solar is to be able to accurately predict it ahead of time. While the traditional electricity generators can be controlled and take minutes to hours to ramp up or down, the renewables are dominated by weather and hence can ramp up and down almost instantaneously, even with the passing clouds. The strong fluctuation in the solar power generation is mainly attributed to the sky's short-term cloud movements. These sky conditions are often categorized as clear, few, scattered, broken, and overcast, and are difficult to capture. On a partially cloudy day, abrupt cloud movements can cause almost 70 to 80% power loss within just a few minutes. In order to deal with this randomness in the solar generation, utilities keep either several generators active or install large-scale batteries, both of which are infeasible solutions. The only way to allow more solar into the grid is to be able to accurately predict its future generation. This stresses both the challenge and a need for the accurate and reliable short-term solar changes. Solar forecast means predicting solar at a future time step based on the predictions of the factors affecting it. Short-term forecasts ranging from minutes to hours ahead can also be termed as nowcasting, while long-term predictions ranging from hours to days ahead can share the umbrella term forecast. Our work focuses on nowcasting. Nowcasting is not a new problem, and there has been many techniques proposed in the past, including numerical weather predictions, statistical learning, satellite imaging, and sky imagery. All of these differ in the forecast horizon, as well as the spatial resolutions, which also determine the data sources and the techniques used. But the existing methods suffer from some challenges, like numerical weather predictions. The classical models which are used to predict weather-based conditions are only appropriate for days to hour ahead predictions and have limited capability to predict smaller cloud changes. While using ground-based sky imagery is site-specific and not scalable because of the need for additional infrastructure like sky cameras. The other way is to use ground-based measurements of cloud cover that are available in the unit of octas, where 1 octa means 1/8 of the sky partially covered in cloud. But even octas suffer from challenges, like octas are coarse and imprecise and fail to capture the phenomenon of cloud dynamics. Not all the solar sites are located next to a weather station, but at a certain variable distance away from it. A new opportunity came by the launch of the GOES 16 satellites by NOAA. These satellites come with new capabilities and much richer and wider set of data, which differs both from the high quality ground monitoring stations and also the previous generation of satellites which it replaces. This data is publicly and freely available free of cost by web-based services and are much more spatially detailed. The special ABI instrument of the GOES senses data in 16 different spectral bands of light for every 0.5 to 2 kilometer square area across the US, while the data is released every 5 minutes. This is opposed to the spatial and the temporal coverage of the ground-based weather stations, which is roughly every 1 hour and for a much bigger area. We further observe that out of the 16 spectral bands released by GOES, it is actually the first 3 channels or the visible bands that are used by the solar panels to convert the sunlight into solar power, while the other channels of the higher wavelengths have the potential to indirectly contribute by either capturing information about cloud properties. The same is reflected in the graph on the right, where we see normalized solar output strongly correlating with the first 3 channels from the satellite. But then the question is, over small time scales, what is the change in these values? With that, we have ascertained that the solar power correlates with the first 3 visible channels of both satellites. We further observe that we also need to look into the amount of change in the solar generation that can happen over a certain time and not just only their absolute generation. Let me illustrate this point by showing the cumulative distribution function of the changes in the solar output at 5:15 and 60-minute frequency for one representative solar site. It is evident that there is not much change at the 5-minute as shown in the blue curve, but more changes happen at 15 and 60 minutes as shown in the green and the red. If we look at the graph on the right-hand side, we show the absolute differences in solar generation between consecutive instants sampled every 15 minutes in the black color. The black curve is well tracked and is in tandem with the differences in the satellite's visible channels shown in the red, blue, and the green curves. This shows that even the absolute changes in the solar generation are in sync with those of the GOES 16 visible channels. These are the 2 key points that we leverage in our solar nowcasting models. Let's talk about them. Let's assume a single solar site of interest as shown in the picture here. Satellite channels contain information in both space, that is the area around the solar site, and time, that is the previous sequence of satellite images. The spatio-temporal dynamics contain information about the atmospheric changes and the cloud movements and is a function of the forecast horizon, that is, how much ahead are we predicting. This rich spatio-temporal information in the satellite data can potentially be effectively used for accurate forecast of site-specific solar generation. However, to learn the end-to-end models, this will require site-specific solar generation data, which is scarcely available compared to the abundant satellite data. Thus, we develop a self-supervised model that uses only abundant satellite data to extract the spatio-temporal information useful for forecasting solar generation. Here is a breakdown of our self-supervised model. Given a set of solar sites of interest, we extract an area tile of, say, W by W around each solar site. Instead of using a single point value at each location, we are now extracting an area of data that captures the movement or the changes in the satellite data. And we extract a time series value of 3 visible channels from the GO-16 satellite for this area in each single site. We repeat this step over 25 solar sites and 1 year to train one single global model. This enables modeling of shared statistical properties across sites rather than overfitting to the peculiar characteristics of an isolated site. This also provides a large amount of data for learning a useful CNN LSTM model, which typically doesn't work well with the small data sets. The satellite data forms a 3D image that we first process using a convolution neural network to extract the spatial features from the image. A CNN model is a standard neural network architecture used for modeling visual imagery and extracting visual features. We then extract a temporal sequence of images over time from the satellite, with the target site always at the center of the image. We vary both the area and the amount, that is, the resolution of the historical data that we use for training, as the optimal values depend on a location's climate and the target forecast horizon. For example, here we show previous 4 satellite images for a region of size 10 by 10 with an interval of 15 minutes between images, or the last 1 hour of changes in the spectral data. We then use one-layer LSTM to capture the evolution of the per instant spatial features extracted from the CNN over time. LSTM is a prominent neural architecture for modeling sequences of data and is also often employed in time series forecasting. The CNN LSTM model is trained end-to-end in an autoregressive manner. That is, given the sequence of the past images, we use the model to compute the predictive values for the next instant. Note that the prediction is a function of both the CNN spatial extraction model and the LSTM temporal extraction model. Given such a trained CNN LSTM model that generates the future satellite observations at a given site, we aim to leverage these predictions in a model for solar nowcasting at any solar installation site of interest. We do this by leveraging a solar modeling framework where we replace the satellite data input with the predicted satellite data from our CNN LSTM model. In a solar modeling framework, we apply a standard ML regression model to a dataset composed of 3 visible channels from the GO satellite, along with the temperature. This approach is entirely black box and implicitly accounts for the site-specific attributes like panel type, tilt, orientation, shading, etc. So in our end-to-end nowcasting models, we take advantage of a globally trained self-supervised model and also the local site-specific solar models. For all our analysis, we use data from 25 solar sites across 2 years, uniformly spread across continental US, including the 2 coasts and the central regions. We average the observations in a 15-minute window that helps to reduce the sequence length for modeling and the noise in the data. This yields more than 300,000 5-step sequences of 10 by 10 images with 3 channels at an interval of 15 minutes. We also collect the solar generation and the temperature data for the same time range. We use 5-fold validation in all the experiments, splitting by day, so that the test sets have the entire day's holdout for evaluation. And we do this for both the channel prediction models and also our end-to-end solar nowcasting models. First, we compare MAPE and the mean absolute error for the forecast. Before we discuss the results in detail, here are some terminologies. Persistence model is a simple past predicts the future baseline, which essentially means that there's no change in solar in the future. Tolerance means the size of the subsequent changes. We compare our results at various tolerances, as predicting largest changes is more difficult. Let's look at some of our results. We first evaluate the simple ML models like decision tree and random forest against the CNN in their ability to predict the future satellite values. We observe that CNN is most accurate in capturing the spatial properties of the satellite data compared to decision tree and the random forest, which were also trained on the same spatial area. Next, we show the same models, but evaluate them on a different spatial area, like areas of say 1 by 1, that is just the solar site, a 3 by 3, a 5 by 5, and a 10 by 10. We see that increasing the spatial area around solar sites results in large improvement in accuracy as reflected on the y-axis. Using a 10 by 10 area gives the best results than not considering any surrounding area from the site, like a 1 by 1. It is also evident that CNN performs much better spatial processing than the other variants of the random forest. We further add LSTM on top of the 10 by 10 area CNN model and utilize the previous time steps as input to the CNN LSTM model. In this case, we use 4 steps, which means we train the model on a data set that includes the previous 10 by 10 spatial regions corresponding to the past 1 hour of spatial observations. The use of the LSTM significantly improves the results in terms of accurately predicting large changes and is twice as more accurate at identifying a change of at least 0.1. We next evaluate the performance of the CNN LSTM variants in forecasting the next time instant channel values. We explore CNN using one-step static image, CNN LSTM using one-step static image, and CNN LSTM using 2, 3, 4 steps into the past. Incorporating multiple steps of information in the CNN LSTM is better than using the current static image for forecasting, showing the utility of a deep autoregressive approach. This signifies that the model is likely able to infer temporal changes in the satellite data, such as the cloud movement, for accurate predictions. Finally, I want to discuss the result from our end-to-end solar nowcasting model, where we combine the predictions of the satellite values with our solar modeling framework to predict the solar generation 15 minutes into the future. Let's briefly cover the comparison matrix. Persistence model is a simple past predicts the future baseline, while the SVR-CT-1 uses the previous instant actual channel values as a naive forecast instead of actual predictions from the CNN LSTM. This works as an upper bound. The SVR-CT works as a lower bound that uses the ground truth observations at the future instant and is not a feasible forecast as that information is unavailable ahead of time. While the CNN LSTM SVR is our proposed model that uses the forecasted channel values from the past values as calculated through the CNN LSTM model. Here is an overview of all the metrics. And here is the end-to-end solar nowcasting result for predicting solar 15 minutes into the future. The performance of our proposed CNN LSTM is close to using the actual future channel values in the model and in between the upper and the lower bound, hence also showing that the approach is useful and accurate for solar nowcasting. I also want to discuss one of our other results, which works as a comparison with other work in the literature. For that, let me introduce you to a metric called skill score, which is a popular metric used to understand the performance of solar forecasting models and is also used by the related work. In this formula here, the error baseline in the denominator is the persistence model, that is the past predicts the future, while the numerator is the error from the model used. A higher score would thus mean that the model outperforms the persistence baseline. Here I'm going to show the average of the skill score on the Y1 axis across all the 25 solar sites at different tolerances as depicted on the X-axis. The blue and the green curve show the skill score calculated over the summer months and the full year data. Our proposed solar nowcasting model improves over the persistence baseline, yielding an average skill score in the range of 14 to 19%. In addition, here is the distribution of the number of data points available on the Y2 axis with respect to the various tolerances through a histogram. The The figure here shows the distribution of the forecast skill score across the 25 solar sites and its variation from 14 to 27%, which is attributed to the different characteristics of every solar site, including the differences in installation capacity, shading, and widely different climates. It is interesting to note here that the prior work done on solar nowcasting using sky camera imagery has a skill score in the range of 10 to 20%, which is only evaluated on 1 or 2 solar sites. Those methods require additional hardware in the form of sky cameras to be installed at every site and hence are not scalable as well as costly. While our approach is highly scalable and applicable to any site across the US. With this, my talk is concluded. Thanks a lot for your attention, and I'm happy to take any questions. Also, feel free to reach out to me on email.